Well, hello there. Now we're going to explore a really interesting and really useful application of the law of sines, and that is a way to actually find the area of any oblique triangle, which is to say any non-right triangle. So I'm going to start off with a triangle here, and I'm going to suppose that I've drawn a perpendicular down from one of the vertices to one of the sides. Now we know that the formula for a right triangle is that area is 1/2 base times height, right? You know that one forever. Well, what we're going to do is treat this side C here as the base, and this perpendicular I've just drawn is a height, h. And so the area of this triangle is now 1/2 C times h. But using some elementary trigonometry, I can see that the sine of angle A is h over b, which makes h equal to b times the sine of A. And if I substitute that h into my area formula, I get the result that area is 1/2 CB sine A. And if you examine this, and if you examine the parts involved, C, B, and A, you can see that I've found a formula for the area of a triangle, any triangle, if I know two sides and the angle between them. It's half the product of the two sides times the sine of the angle between them. So that formula could also be expressed as 1/2 AB sine C, or 1/2 AC sine B. In each case, I've got two sides and the sine of the angle between them. So this is going to prove to be a very useful formula for us, as you'll see. But before we actually apply it, we might take a moment and examine the issue of what happens if the triangle is obtuse. In that case, how could I possibly apply that same formula? Well, if this is a height drawn, and this is my normal geometry tells me that the area is still going to be 1/2 C times H, C being the base and H being the segment drawn perpendicular to the line containing the base. And now if I notice here, the sine of this angle A is I'm really dealing with the sine of this angle. So the sine of A is once again H over B. And once again, I can make that same substitution that H is B sine A, so that area equals 1/2 CB sine A. It's the same exact result, even if I have an obtuse triangle. So let's go ahead and try this on for size. Here's an SAS situation. We're given that little a is 12 and little b is 15. And we're given the measure of the angle between them. C is 75 degrees. So we apply our formula that area is 1/2 12 times 15 times the sine of 75. And then you can make sure your calculator is in degrees mode and go ahead and work it out and see if you don't get the same thing I got, which was 86.9 square centimeters. So just round it off to square centimeters. This one's a piece of cake to apply. We also have another formula, and this one is not easily proved or demonstrated. In fact, if you wait until after the next video on the law of cosines, you could then find the page in your book that has a full proof of this if you really want to look at all the gory details. This is going to be one we're just going to assimilate and use. But it's pretty interesting, and I'm going to prove that it works for you by taking a triangle whose three sides are known, and I'm going to make it a right triangle. So I'm going to suppose that I was given a right triangle and the sides were 5, 12, and 13, and I want to find the area of that. Well, I can use my 1/2 base times height formula on this one. And so that's easy to see that that area is 30. And when there are no units specified, the answer is unitless, but it would obviously be 30 of the square, or whatever the units that 5, 12, and 13 are. Now, here's another way to find that. Some would say a more interesting way. What if I took the three sides and added them together? 5 plus 12 plus 13, and divided that by 2. And I'm going to call the result that I get of doing this S. I'm going to call it by the letter S. And it's not too hard to see that in this case S is 15. You can verify that if you want to. Well, then I'm going to claim that the area of this triangle can be found by taking the square root of that S times S minus each of the three sides of the triangle in turn. 15 minus 5 times 15 minus 12 times 15 minus 13. And you can work this out with me. It's 15 times 10 times 3 times 2. And it's not too hard to see that that turns out to be 30 also. Now, that's just not really a proof of anything. And you might say, well, gee, that was a lot of work to get, what was pretty easy to get up here. But the key is that this formula that I just used, this method that I just used here in these two steps, works for any triangle that's oblique, whether it's, works for any triangle, whether it's right or oblique. And in order to see that, first I want to state the formula. It's called Heron's formula, named after the Greek mathematician who discovered it. And it says the following: if the sides of the triangle are A, B, and C, then S is A plus B plus C, all divided by 2, and that the area is the square root of S times S minus A times S minus B times S minus C. So it involves some computation to apply this, but it works. And so let's go ahead and figure one of these out using this formula. Pause the video actually and try this, and then when you've got something, you can come back and try it. So first, now that you're back, did you get that S was, did you compute S as 31 plus 52 plus 28 all divided by 2? And then when you plug that into Heron's formula, you should have gotten 361.77, roughly, approximately rounded off. 361.77. This is just calculator work. This isn't a, there's not a lot of thinking involved. It's just a matter of plugging things into the right places. Okay? Sounds good. Hope that was easy for you. Now here's one for you to do to hand in. I'll leave it to you to figure out the method you're going to use to attack it. The challenge in this one is to solve it without using a calculator. That's how you'll get the full 5 problems for this, is to do it without using a calculator. But that angle, 120 degrees, will be pretty easy to work with. So good luck and happy calculating.